Good morning, chemistry. Mr. McKee here, and I want to talk to you today about limiting reactants, which is, as it says, an application of stoichiometry. So we're going to begin with a scenario. We want to make some s'mores, all right? So take a look at what is essentially our equation up here, and this has a lot of things in common with a chemical equation. It's also more commonly known as a recipe, right? So the recipe is you need 2 graham crackers, 1 square of chocolate, and 1 marshmallow to make 1 s'more. At least this recipe. Now everyone has their own particular type of s'more that you make, but this is kind of the old school basic s'more recipe, all right? So these numbers in front of the ingredients, we can think of these as the coefficients, and they're like the coefficients in a chemical equation. They give us the ratio. So we have a 2 to 1 to 1 to 1 ratio up here, which means we need 2 graham crackers for every 1 square of chocolate and 1 marshmallow, and those will all make 1 s'more. So everything on the left side of our arrow up here, as a reminder, these are our reactants. I'll label those R, and then everything on the right side, this is our product. We only have one product in this case, and that is what is made in the reaction. Okay? So now consider a scenario. Consider that you got some friends coming over, and you look in your closet, and these are the ingredients that you have in your cupboard, I should say. You have 12 graham crackers, 7 squares of chocolates, and a whole bunch of marshmallows. This is probably pretty typical since marshmallows come in the big bags. You got 100 marshmallows, all right? So how many s'mores can you make? Well, the answer, if you take a look at this, if we are sticking to our recipe above, sticking to those ratios, which are 2 to 1 to 1 to 1, the answer is you're only going to be able to make 6 s'mores. And the reason for that is the graham crackers, okay? The graham crackers limit our number of s'mores because we've only got 12 and you need 2 graham crackers per s'more, so that means you can only make 6. Now, if you're just looking at the squares of chocolate, you could make more s'mores if you had more graham crackers, right? You've got enough chocolate to make 7 s'mores, okay? And you got a whole bunch of marshmallows here. You could actually make 100 s'mores with that many marshmallows, all right? But a s'more requires all 3 ingredients, so based on that, we can only make 6. So this introduces us to a couple vocab words here. We say in a scenario like this that the graham cracker is the limiting reactant because it is limiting, in this case, how many s'mores we can make. The chocolate and the marshmallows, in this case, because they are in excess, we say these are the excess reactants. We've got more of those than we need. Again, if we were just looking at marshmallows, we could make 100 s'mores with that many marshmallows, and we could make 7 s'mores with that much chocolate. But we only have 12 graham crackers available to us, so that limits us to 6. So, limiting reactant, we have 1 in this case, and then we have excess reactants. So, let's move into the actual chemistry here, but keep kind of going back in your head to that example with s'mores, because that introduces the basic concepts. So these are the steps that we're going to follow when we're solving problems about limiting reactants. I'm not going to read all these to you, but the first one I am going to emphasize that when we're reading the question, which is really important to read it carefully, we want to label reactant 1 and reactant 2 and our product of interest. You might have multiple products in most cases, but we're always going to be interested in one of those products. And as far as which is reactant 1, which is reactant 2, it doesn't really matter. I usually just list them in order. So I'll show you how to do that in our example here, and I'll walk you through these other steps. So our first example problem, what mass of CO2, so that is what we're trying to solve for, so I'll put a question mark there, can be made when 30 grams of oxygen react with 25 grams of C2H5OH, which is ethanol, according to the following chemical equation. So I'm going to label my first reactant in the equation as R1. Again, it doesn't really matter which one you label R1, but it's nice to be consistent every time so you don't get confused. And I'm going to label the second reactant R2. And our product of interest, the thing we're trying to figure out, is the mass of CO2. So I'm going to go ahead and label that as P. And we don't really care about water here, so you can cross that out if you want. That is not relevant to this particular question. So we've got fairly complex tables here, so you're going to want to get comfortable with using those, and they're to help you stay organized. So reactant 1, as we said up here, is going to be C2H5OH, which is ethanol. And we've got 25 grams of that. I got that information from the question itself. And my conversion factor that I'm going to use, because we're going to have to convert from grams of ethanol to moles of ethanol. So my conversion factor is going to be the molar mass of ethanol, which is 41.029. And that is grams. So 1 mole of ethanol has a mass of 41.029 grams. So that's going to be my conversion factor. So I'm going to go ahead and make my conversion that I'm going to need here. I'm going to have to convert my mass in grams of ethanol into moles. So this is going to be my starting number, 25 grams of ethanol, C2H5OH. And I'm going to multiply by my conversion factor. I'm going to put grams on the bottom so that I can cancel it out. So that's 41.029 grams, and I'm going to put 1 mole on top. And again, that enables me to cancel out the unit grams. I can ignore that 1 there, so I'm going to divide 25 by 41.029. And when I do that, I get 0.58 moles of C2H5OH, also known as ethanol. So I just figured out how many moles of reactant 1 I have. That's always going to be my first step. Reactant 2 is oxygen, and I have 30 grams of that, which again I got from the question itself. The molar mass of O2 is 1 mole of O2 equals 31.998 grams. So just like with reactant 1, I'm now going to convert my mass of oxygen in grams into moles. So I'm going to put grams on the bottom, 31.998 grams, and that's equal to 1 mole. Of course, that enables me to cancel grams out, and I'm going to divide 30 by 31.998. Pause the video if you need to check your calculator skills. Okay, your answer should be 0.94 moles of O2. So, in this particular case, and you can think about this, compare this to like graham crackers and chocolate, this is the amount of reactants that I have. I've got 0.58 moles of C2H5OH, and I've got 0.94 moles of O2. So that's how much we have to work with. So the math is a little bit more complicated than with the graham crackers, but I'll show you how to use this information now. So my moles of reactant 1, we just figured out, are 0.58, and my moles of reactant 2 are 0.94. And my ratio of these two, I'm going to get from the equation. So for ethanol, C2H5OH, I have a 1 here. Remember, if there's no number, that's the same as a 1. And for oxygen, my coefficient is a 3. So my mole ratio is 1 mole of ethanol is going to go with 3 moles of oxygen. Again, that is like saying 2 graham crackers for every 1 square of chocolate. It's a similar statement there, okay? So the next thing we're going to do is we're going to see if we're starting with this much of reactant 1, we're going to see using this mole ratio how much of reactant 2 I'm going to need. So this is like saying if I've got 12 graham crackers, how many squares of chocolate am I going to need? Okay. So we're going to put 0.58 down here in our train tracks. That's going to be our starting unit. And that's moles of C2H5OH. And I'm going to multiply that by my mole ratio. So I'm going to put C2H5OH down here on the bottom. And that is 1 mole of C2H5OH. And on top, I'm going to put 3 moles of O2. And when we arrange it like that, of course, I can cancel out moles of ethanol. And I'm going to be left with moles of oxygen. So I'm going to multiply 0.58 by 3 and hit enter in my calculator. And what I find out, and actually I'm going to put my answer right here where it says moles of reactant 2 needed, is that I'm going to need 1.74 moles of O2 to go with 0.58 moles of C2H5OH. All right. Now we're going to look at how much I actually have. We're going to compare here. So I need 1.74 moles of O2. But when I look up here in the top right, I see that I only have 0.94. So I don't have enough, in other words. So that means that the amount of oxygen I have is going to limit how much of the product that I can make. So my limiting reactant is oxygen. So this is like figuring out that if I've got 12 graham crackers and 1 square of chocolate, that my amount of chocolate is going to limit how many s'mores I can make. This is very similar to that. Okay? So now that we know what the limiting reactant is, we can figure out how much of the product we can make. So we're going to come down to the bottom portion of the table. And the first thing I'm going to write is my mole ratio of the limiting reactant to product. So let's go back up to our equation. And oxygen is my limiting reactant. I've got 3 moles of that. And my product of interest is CO2. So I've got 2 moles of that. So we've got a 3-to-2 ratio there. So let's write that into the bottom here. 3 moles of O2 go with 2 moles of CO2. That is my ratio that I'm going to use. So again, we know that the amount of oxygen is our limiting factor, so I'm going to put the amount we have right here as my starting unit, 0.94 moles of O2. And I'm going to start by multiplying by my mole ratio. And of course, I want moles of O2 on the bottom because I'm trying to cancel that out. And we're converting into moles of CO2. So my ratio again is 3 moles of O2 for every 2 moles of CO2. So this allows me to cancel out moles of O2. And now I need to figure out how much mass of CO2 I can get out of this. So I'm going to have to convert from moles of CO2, which I'm going to put down here, into grams of CO2. For that, I'm going to use my molar mass of CO2, which is the product. So I'm going to write that down here, 44.009 grams. You'll have to add that up on a separate piece of paper. And so I'm going to put that into my table. And that is my basic setup. My product of interest, of course, is CO2. So when we arrange it like this, I can now cancel out moles of CO2. And that's going to leave me with my answer as grams of CO2. So the way we plug this into our calculator is 0.94 times 2 times 44.009 divided by 3, enter. And when you do that, you should get 27.58 grams. So that's the amount of carbon dioxide we can make when we have the amount of reactants described here. So pause the video and see if you can do this with the U-Try. Welcome back. Hopefully you were successful with the U-Try, but let's go through the solution here. So in this case, the question says we've got 45.8 grams of K2CO3. Those are added to 97.4 grams of HCl. So those are my two reactants. K2CO3 is reactant 1, HCl is reactant 2. And the question is, how many grams of KCl, that's what I'm trying to solve, can be produced? So KCl is my product of interest. I don't care about water or carbon dioxide in this case, so you can cross those out if you want. So I'll move a little faster on this now. So reactant 1 is KTCO3, and we've got 45.8 grams. I get that, of course, from the question itself. My conversion factor is going to be the molecular mass of K2CO3. You'll have to add that up on a separate piece of paper. We already have a lot of tables here. So that is 138.204. All right, and now we're going to convert our grams of KTCO3, which is 45.8, into moles. So I'm going to put my grams on the bottom so that I can cancel it out. 138.204. 1 mole on top. That allows me to cancel grams. And when I plug that into my calculator, I get 0.33 moles of KTCO3, K2CO3. Okay, so that's how much of reactant 1 we have in moles. Reactant 2 is HCl, hydrochloric acid. And we have 97.4 grams of that. So 1 mole of HCl is going to be equal to 36.458. Again, you'll need to add that up on a separate piece of paper. So let's convert our starting mass into moles. Again, I put grams on the bottom so they can cancel out. And then I divide, and I get 2.67 moles of HCl. So now we know how much we have of each reactant in moles, which is what we need to know. So let's move into our solution part of things now. So the moles of reactant 1, we figured out 0.33. The moles of reactant 2, is 2.67. Okay, so the mole ratio of those two I get from the chemical equation, and it's going to be 1 to 2. So for every 1 mole of K2CO3, I have 2 moles of HCl. So we're now going to try to figure out if we have 0.33 moles of reactant 1, and we need to combine things at this molar ratio, how much of reactant 2 am I going to need? And I'm not asking how much we have, we already figured that out, but I'm asking how much do we actually need. So let's put our moles of reactant 1 down here. And to make things a little simpler here, I'm just going to write R1, so I don't have to write out that whole formula for K2CO3. So my molar ratio, I'm going to put 1 mole of R1 down here, and then I'm going to put 2 moles of HCl up here because that is my molar ratio. This allows me to cancel out moles of R1. And what I figure out now is that I have 0.66 moles of HCl is what I'm going to need. So I'm going to put that right here, needed. And And now we're going to compare what we need, which is 0.66 moles, to what we have, which is 2.67 moles. We have more than we need, which means that K2CO3 is the reactant that is limiting how much product we can make, okay? Because our HCl is in excess in this case. We've got more than we need, which means the other reactant is going to be our limiting reactant. So write that over here, K2CO3, which is reactant 1. Now moving down, let's figure out, now that we know what our limiting reactant is, let's figure out how much product we can actually make. So my mole ratio of the limiting reactant to product is, let's come back up here to the equation. I've got 1 mole of K2CO3 for every 2 moles of KCl, which is my product of interest. So first of all, I'm going to write down my product of interest down here, KCl. It's got a molecular mass of 74.548 grams. And my mole ratio, we just said, was 1 mole of K2CO3 for every 2 moles of my product of interest, which is, again, KCl. So I'm going to put my starting amount of my limiting factor down here, and it's 0.33. And that is K2CO3, kind of a lot to write. And I'm going to begin by multiplying by my mole ratio. So I'm going to put moles of K2CO3 down here. And I'm going to put moles of KCl up here, my product. And the ratio is 1 mole of K2CO3 for every 2 moles of KCl. But I'm not done because I'm trying to figure out the mass in grams of my product that can be made. So I can cancel out moles of K2CO3 here. Now we need to convert to grams of KCl. So for every 1 mole of KCl, I've got 74.548 grams of KCl. Arranging it like this allows us to cancel out moles of KCl. I plug everything into my calculator and I get 49.20 grams of KCl. So with the amount of reactants described in the problem, that's how much of the product we can make. So as always, thank you for watching. Reach out if you have any questions, and have a great day.